All right, Lewis structures, taking into account formal charge. Yesterday, I made a video of the Lewis structure of sulfur dioxide, and it looked something like this. That sulfur was single bonded to one oxygen atom and double bonded to the other oxygen atom, and we made sure that the octet rule was complete or satisfied for each atom, and voila, here we have the Lewis structure for sulfur dioxide. It does of course have the resonance form with the oxygen on the right double bonded instead of the one on the left, so essentially a mirror image of what I have here, but there we go, two resonance structures of the Lewis diagram for sulfur dioxide. Now, this does not take into account formal charge. That's a bit of an extra step. So let's take a look at that. So, what exactly is formal charge? Well, it's a charge assigned to an atom in a molecule, assuming that electrons in all the bonds are shared equally between the atoms, regardless of relative electronegativity. Formal charge is an imaginary charge that's used in the molecular stability analysis. It's not the actual charge that an atom has. The formal charge is calculated as the number of valence electrons minus the number of non-bonding electrons, we'll call it N for non-bonding, and then also minus the total number of electrons shared in bonds. So let's put that as B over 2, because of course a bond is 2 electrons but 1 from each atom. So if we go back to the Lewis structure that we had a few moments ago, sulfur dioxide, let's take a look at the formal charge of the oxygen atom on the left. Formal charge is given by the number of valence electrons. So that oxygen on the left, of course, that brought in 6 valence electrons. Its electron configuration or electron arrangement was 2, 6. So that tells us it has 6 valence electrons. Now, we subtract from this the number of non-bonding electrons. Well, we have 2 here, we have another 2 here, so we're going to subtract 4. But then we also subtract the total number of electrons shared in bonds. Well, that would be 1 from this bond and 1 from that bond. Remember, a bond is 2 electrons, but formal charge considers the electrons shared equally between the 2 atoms. So 1 on the oxygen side and 1 on the sulfur side. Another way, I guess you could think of it, is that the formal charge is the number of valence electrons minus the number of non-bonding electrons minus the number of bonds. So it's usually given like this: the total number of electrons shared in bonds, and then that's divided by 2. Actually, let's just go back here. The total number would be 4. Electrons shared in the bonds would be 4, but then we divide it by 2, so we're taking away another 2. But what we could actually think of it as just the number of bonds. So we've got 6 minus our 4 non-bonding electrons minus the 2 bonds that we have. Anywho, that is going to come down, of course, to 0. So that oxygen atom on the left has a formal charge of 0. That's lovely. That's actually what we want. We want to minimize the formal charges as much as possible. If we take a look at the sulfur atom, sulfur also had 6 valence electrons. We subtract the number of non-bonding electrons, and there are 2 of them up above the sulfur there. And then if we subtract the number of bonds, we have another 3. Remember, we can say the number of bonds. It's the same as the total number of electrons shared in bonds, but then that's divided by 2. So that gives us the number of bonds. And when we do this maths, we come out with 1. So the sulfur atom actually has a formal charge of 1, or positive 1. In fact, let's write the formal charges of each atom. Cool. Let's look at the other oxygen atom. Like the first one, it had 6 valence electrons minus the number of non-bonding electrons that it has, and there are 6 of them, minus the number of bonds. There we go, and we get an answer of, well, what happened there? Don't know. Anywho, we get an answer of minus 1. So let's write that up there. So these are the formal charges now of the atoms with this Lewis structure or Lewis diagram. Now, the thing is, with formal charge, Ideally, we want the formal charges to be 0. And for one of them, yes, it is, and for the others, they're not. Now, they don't have to be 0, but we really want them to be 0. Now, we can actually make the formal charges 0 for this molecule, because the thing is, there are certain elements, sulfur being one of them, that can form resonance structures that expand past their octet in order to lower the formal charges on each element in the bond, each atom in the bond. Now, not all elements can expand their octet. It depends on their ability to access the d orbitals to expand their valence shell. Only elements in period 3 or higher have that d orbital and can accommodate more electrons. Sulfur is one of those that can. Now, in this Lewis diagram here, each atom has satisfied the octet rule, but in order to bring the formal charges to 0, what we can do is grab these non-bonding electrons and let's just make a bond with them. Now, we can see that actually sulfur now, the octet rule isn't satisfied. It's expanded its octet. But if we take a look at the formal charge of each atom, well, the first oxygen, nothing has changed. In fact, let's just do it again anyway. It had 6 valence electrons minus the 4 non-bonding electrons, minus, we see 2 bonds there. That's a formal charge of 0. Grand. Let's list it there. Now we'll take a quick look at the sulfur. Had 6 valence electrons, minus the non-bonding electrons, there are 2 of them, minus the number of bonds, we can see 4. And so what we see now is that the formal charge of sulfur has come down to 0. Grand. Where formal charges are concerned, that's what we want. We want to get them as close as possible to 0. The other oxygen, the one on the right, brought in 6 valence electrons, minus the 4 non-bonding electrons, minus we have 2 bonds there, and that now also has a formal charge of 0. So you can see by adding another bond and making that also a double bond, like the one on the left, all the formal charges are 0. This actually makes the molecule more stable. So this is what we would actually end up with as the Lewis structure for sulfur dioxide when we take into consideration formal charge. Now, formal charge is a bit of a step up, it's a bit of a higher level than your standard Lewis diagram. So if you've been taught formal charge, grand, here's the Lewis structure. If you haven't been taught formal charge, then go with what I had earlier with just a single bond to one of the oxygens and a double to the other. Because here's the thing. Formal charge, this is nice for theory. This is what theory suggests, hey, this molecule would be more stable. But what do we actually see in practice? Well, if we take a good look at sulfur dioxide, what we see is in fact this version with the 2 resonance forms. So the theory suggests, hey, the Lewis structure for the most stable form of the molecule will be sulfur double bonded to each oxygen, but in practice what we actually find is the resonance forms of this version here with 1 double bond and 1 single bond. So yeah, formal charge gives us what we think we should get, but what we actually get is this other version. Anywho, that's formal charge with Lewis diagrams. Well, that's the video done. If you liked it, brilliant. Hit the like button and leave me a comment too. Now you know what to do. Go hit that subscribe button. We'll see you next time.